It's 2 in the morning. A tanker truck eases into an empty gas station, air brakes hissing, no customers, no fanfare. The driver steps down, walks to a small metal cover, flush with the pavement, connects a hose, and opens a valve. Then thousands of gallons of gasoline begin disappearing silently into the ground. Most people assume they understand exactly what happens next. Tank underground, pump above ground, hose in the car, simple. But that assumption skips over one of the most carefully engineered fuel systems on Earth, a system managing explosion risk, vapor pressure, chemical containment, and precision measurement simultaneously. Everything familiar about a gas station is hiding something most people have never once thought to ask about. Start with the obvious assumption: the gasoline is stored underground to save space, or because there's nowhere else to put it. That instinct feels right. It's also wrong. The reason gasoline goes underground is thermodynamic. Soil temperature, 4 to 6 feet down, stays between 50 and 60 degrees Fahrenheit year-round. In Arizona in August, in Minnesota in February, it barely moves. Gasoline stored at those temperatures stays denser, produces less vapor pressure, and evaporates far more slowly. And here is the critical part. Gasoline doesn't explode as a liquid. It explodes as a vapor mixed with air. The cooler the fuel, the less vapor it releases, and the safer the entire site becomes. The ground is not a hiding place. It's a passive climate control system running constantly, without a single moving part. Above ground, that logic inverts. A metal tank in direct summer heat absorbs solar radiation, warms the fuel inside, and generates vapor pressure the entire system then has to manage. The tank that looks more accessible is actually the more dangerous version. Most people picture the underground tank as a thick steel drum, a buried cylinder, sealed ends, solid walls. That was the standard design for most of the 20th century, and it failed quietly for decades before anyone fully understood what was happening. Modern underground storage tanks are built on a completely different principle: double wall construction, an inner tank that holds the fuel, surrounded by an outer shell that holds nothing but monitored space. The gap between those two walls is continuously watched by sensors. If the inner tank develops even a small crack, fuel or vapor enters that interstitial space. The pressure signature changes. An alarm triggers. The system doesn't have to fail catastrophically to be detected. It just has to disturb that narrow, instrumented gap. The material changed too. Steel corrodes. It reacts with fuel chemistry, with water infiltration, with soil over time. Modern tanks are predominantly fiberglass composite, chemically inert, non-conductive, immune to the corrosion that silently compromised single-wall steel tanks over decades of use. A typical station has 3 to 6 of these tanks installed underground, each holding 10,000 to 30,000 gallons, buried beneath ordinary pavement that most customers cross without a second thought. Here is something about gasoline most people have never considered. It doesn't sit still. Even in a cooled, sealed tank, gasoline is constantly generating vapor, lighter hydrocarbon molecules moving toward the gas phase, building pressure against the tank ceiling, looking for any exit point. Gas stations manage this with vapor recovery systems. There are 2 stages, and most people have directly interacted with both without knowing it. Stage 1 happens at night when the tanker arrives. As fresh fuel pours into the underground tank, the vapor already sitting above the fuel has to go somewhere. In older systems, it vented directly into the air above the station. In modern systems, a second hose runs from the tank back to the tanker truck. Displaced vapor travels up and back into the truck. Nothing escapes. Stage 2 happens at the pump. That rubbery collar on the nozzle, the sleeve that presses against the vehicle's fuel inlet, is not just a seal. It is an active vapor collector. While fuel flows in, vapors rising from the car's tank are captured and routed back underground. The nozzle is simultaneously delivering fuel and recovering vapor through a second internal channel. Almost no one notices because there is no reason to look. Before these systems were mandated in the 1990s, gas stations were among the largest sources of ground-level volatile organic compound emissions in American cities. The familiar smell of a fill-up was not inconvenience. It was measurable pollution produced at millions of fuel events per day. The common assumption is that the dispenser above ground pulls fuel up from the tank below. There is a pump involved, but it is in the wrong location in most people's mental picture. Most modern stations use a submersible turbine pump, a motor and impeller assembly sitting inside the underground tank itself, submerged in fuel. It pushes from below. Pushing a liquid upward through a sealed pipe is far more efficient and reliable than trying to create suction across a long vertical run. The dispenser cabinet on the surface the machine customers interact with is not a pump. It is a metering station. The price display is driven by a precision flow meter inside the cabinet, counting fuel passing through the line in real time. At the base of every dispenser is a shear valve, a breakaway coupling engineered to fail clean. If a driver leaves with the nozzle still inserted and pulls away, the valve separates at its designed failure point, sealing both sides instantly. No spill, no ignition. It happens more often than most people realize, and the engineering absorbs it every time without incident. The nozzle's automatic shutoff is one of the most trusted pieces of safety hardware at any gas station. And almost everyone's explanation of how it works is wrong. The assumption is a pressure sensor, that the nozzle somehow detects a full tank, registers the back pressure, and cuts the flow. There is no pressure sensor. There is no electronic signal. There is no communication between the nozzle and the vehicle whatsoever. The mechanism is purely pneumatic, and it has worked the same way since the 1930s. Near the nozzle tip, there is a small hole. That hole connects via a narrow tube to a venturi chamber inside the handle. While the tip is above the fuel surface, air flows freely through the hole, and the venturi effect generates a slight negative pressure that holds the flow valve open. When rising fuel submerges that hole, airflow stops. The pressure differential collapses. A diaphragm inside the handle mechanically trips the shutoff lever. The flow stops. No electronics, no sensor, no tank awareness at all. It's a self-contained air pressure trick built into the geometry of the nozzle, running on the same physical principle as a carburetor. It has not needed a fundamental redesign in nearly a century. For most of the 20th century, none of this safety architecture existed in any regulated form. Tanks were single-wall steel. There was no mandatory leak detection, no vapor recovery, no monitoring standard. And the consequences accumulated invisibly underground for decades. By 1984, the EPA had documented something that became impossible to ignore. Roughly 1 in 4 underground storage tanks in America was already leaking. Not at risk of leaking. Already leaking. MTBE and benzene, both known carcinogens, were appearing in drinking water wells across the country, migrating through soil from corroded tanks installed in the 1950s and never once inspected. In 1988, the EPA issued its underground storage tank regulations, mandating double-wall construction, active leak detection, and vapor recovery. The engineering architecture of every modern gas station is largely a direct answer to that single moment of documented failure. The familiar, unremarkable station of today was built, in large part, by regulation written because the previous design was silently poisoning groundwater at scale. Walk the surface of a gas station with this in mind, and it becomes a different place. Those small metal caps flush with the concrete, fill ports, vapor return ports, monitoring access points. The entire underground system surfaces through a handful of round metal discs in the pavement. The color-coded dispenser handles are not branding. They are federally standardized to prevent misfueling, green for diesel, specific codes for different gasoline grades, a system designed largely around the consequences of putting the wrong fuel into commercial equipment. The vent pipes rising above the canopy, usually 12 feet or higher, are pressure relief points for underground vapor. If pressure builds past threshold, vapor exits high and dispersed well above any ignition source at ground level. The raised concrete pad under each dispenser is secondary containment. Any surface spill pools on that pad instead of reaching soil. And the red emergency stop button near the cashier cuts all submersible pumps simultaneously. One press, total fuel shutdown, no deliberation required. None of this is a perfect system. Vapor recovery collars wear down. A degraded seal means vapor escapes at the nozzle on every single fill. Some stations, under regulatory grandfather clauses, still operate pre-1988 infrastructure. The submersible pump model has no redundancy. If the underground pump fails, the station stops. Ethanol-blended fuels, now the standard in most markets, are more corrosive to older seals and carry higher vapor pressure than pure gasoline. The original engineering did not fully account for that. The system works, but it works inside the gap between engineering design and the operating reality of thousands of stations running aging equipment under variable maintenance schedules. That tanker at 2 in the morning, the driver connecting that hose to a metal cap in the pavement, that is the entry point to all of it. Thermodynamics, vapor chemistry, pneumatic physics, environmental containment. The cap is flush with the concrete. The engineering runs 10 feet straight down. The fuel in that tank was refined hundreds of miles from where it sits now. The pipeline system that moved it there operates on one of the most counterintuitive pressure principles in industrial engineering, and that system is at least as invisible as this one.